first case, we pulled the little cart of science up the incline plane, and this was our start position, this is our stop position, and you guys did a good job of measuring from same place to same place, and you got a nice distance that it traveled, and you were reading the force there. Now, what I see around the room is that you guys have a force distance graph that kind of looks boring, just a nice flat line. Boring, but lots of information. What's the slope of this line? About what? About 0. Okay, so I had a nice constant force. That means that the forces were balanced. Remember, that's measuring, the spring scale is measuring the force that you were applying. But what other forces were acting on that inclined plane? There's a gravitational force, and this is an inclined plane, right? So that had an x component and a y component on the inclined plane. There's probably a little bit of friction because it's not perfectly frictionless. It's very, 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 very close to being frictionless because of the fancy wheels and stuff on these little pass cars. So let's look at some data. And I walked around the room and I was looking at some numbers. And so Justin, all back there alone in the back. What was the force when you pulled it up the incline? What force did you measure? 0.55 newtons when it was up the incline? And what distance what was the final distance you pulled it to along the incline? 1 meter? Okay, so I got 1 there. And then when we pulled it or picked it straight up off the table so that it ended up in the same place, Justin, what force did you apply when you just picked it straight up? 2.5 newtons. And what distance did you pull that force through? 0.2, yeah, so 0.23 meters. Any questions so far? All right. Now these two, so I see some similar things about these two graphs. The slopes of both of them are 0. And when you were graphing before, for a velocity time graph, we did 2 things that were really important. What did we do? Do you remember what you could find with a velocity time graph? We could definitely find the acceleration by doing what? What was that special thing to do to the graph? Find the slope, all right? Now what about when, what was that other thing that we did to it? There was another thing that you could do with a velocity time graph that was important. Find the slope of the line. They gave its acceleration. The area under the curve, right. So there are 2 things that you can do with most graphs. If you're ever trying to figure out what is this graph giving me or what kind of information can I find from this graph, look at the slope and look at the area under the curve. Because one of those 2 things is probably important. Now these 2 forces are different and the distances are different. The slopes are the same. And what's that other thing I could probably look at? The area under the curve, the area under the line. What would the area be under this line versus the area under that line? Are they really close, super close to being the same? So they're really close to being the same. So let's look at that value here. So area, and that would be what, 0.55, really boring, times 1. What do we get, 0.55? And we don't forget units, so what would this unit be? What did we just do? We multiplied what times what? A force times a distance, so it should be Newton meter. Okay? Now what about the area? So let me shade that in. There's our area there. Now let's find the area under this portion over there. So our area, our force was what? 2.5 times 0.23. So what's the area under that curve? So 0.575. Would the units be the same? Newton meter? What do you think about these 2 values right here? These are experimentally found numbers. in this lab-like experiment where we weren't doing very, very super precise measurements because we were using meter sticks and force measurers that are just spring scales. We weren't using computers and things like that. We were using your brain. What do you think about those two numbers? Are they close enough? Or are they just too far away? I think they're pretty much the same. So I applied a different force and different distances and got the same something from that, same Newton meter from that application. So the work done when a force is applied, work is done when force is applied through a distance. So work is done when the force is applied through a distance. And that force must be parallel to the distance. And let me show you why. Tante, just kidding. So a Newton meter is the same thing as a joule. It's capital J if you're abbreviating it, just trivial. It's little J-O-L-E if you're spelling it out, because it's no longer a person. It's a unit, just so you know. So you can abbreviate it with a capital J, though. I know, very confusing, isn't it? All right, so now my question is, how much work is done on this little box of science? So here it is, little mass. And if I apply this force that is parallel to the floor, in terms of F and D, how much work do we do? What do you think? Yeah, work would be the force times the distance. So far so good? Easy cheesy lemon squeezy? What if this is like a wagon or something, you're pulling it up and to the right? So instead of pushing my cart, I'm pulling my cart. I need the X component, and if I have the angle to the horizontal, so if I've got the angle measured to the horizontal, I need this X component right there. And that X component would be the cosine function. So F cosine theta times D. Now be careful that when you're punching this stuff in your calculator that you don't multiply F times the cosine of theta times D, but that you do the force times the cosine of theta times D. Do you see the difference? Because of that, sometimes you'll see in a textbook where the D has been put in front of the cosine, just so that you don't make that mistake. So if you ever see FD cosine theta, it's just the D has been moved to reduce calculator finger punchy errors. Okay? Now what about the case where I pick the object straight up? What do you think, Nathan? There's no work done in terms of physics. Do you get tired? Well, if I pick it straight up, my force and my distance will be parallel. So sure, I'm doing some work. But while I'm holding it up, so I picked up my laundry basket, right, and I'm walking. The force I'm applying is straight up. But the distance that it's moving along the floor. In terms of physics, are we work on that basket? There is when we first pick it up. There's no work in the Y direction. There's no work in the X direction in this case. So, say well, in any case where the angle is 90 degrees. Because what would the cosine of 90 be? 0. So actually, the work done when the force is perpendicular to the distance, there's no work done. And you don't like an answer that's 0. You just don't like it. But a lot of times, this concept is tested. by me because it's important, and on the AP exam because it's important. And so it's okay for the work to be 0 if the force is perpendicular to the distance. But you don't like an answer of 0, so you will do your best to come up with some made up answer. Please don't do that. Please be okay with sometimes the answer is 0. Now, to make a point of clarification, if same box, I can't get to my little box there. Here we go. Same box, same force, but now I'm going to pick it straight up D. So I think this might help that differentiation. Okay, has work been done to that box? That force is parallel to that distance, so we can do work in the y direction. So that would be force times distance. There. Now, the cool thing about work or energy, because when work is done, it causes a change in energy. So they are interchangeable. Sometimes when you read a question, if you substitute the word energy in for the word work, it'll make a lot more sense in your head to think about what was the work done, or what was the energy change. So you can kind of swap them out that way. So when you put energy into a system, whether or not it's gasoline into your car or food into your body, or dragging the cart up to the inclined plane, does that energy have a direction? When you put gasoline to your car, is that gasoline like negative gasoline or positive gasoline? Not in terms of direction. I mean, I guess you can add and then subtract, but so what kind of quantity is one that doesn't have direction? It's a scalar. So we can either add energy to a system, we can either do work on a system, or we can take energy out of the system, transfer it to other forms of energy, or work is done by that system. Okay, so work is a scalar. Both of these guys are a scalar. How do we add scalars, just to remind you? If you have 5 joules, and then we're going to add 6 joules, how many total joules of energy do you have? 11 joules. The beautiful thing about scalars is you just add them together. What if you have 7 joules and 3 joules were transferred to other forms? So maybe sound or light or some other form of energy. Oh my gosh, we'd have 4 joules left over. So for scalars, you just add them up. It's going to be lovely. You're going to get out of practice of doing vectors pretty much, and then we'll have to jump back in them.